Hi, welcome to the 6th episode of the Quantum Physics series. Solar cells, your selfie camera, and the James Webb Telescope all have something in common. Today, we will take a look at one of the biggest breakthroughs in physics from the last century, the photoelectric effect. During the 1800s, some physicists, such as Becquerel, Willoughby Smith, and James Clerk Maxwell, began to describe the relationship between light and electricity. In 1888, Heinrich Hertz and Wilhelm Halbwachs discovered that focusing ultraviolet light on a clean zinc or selenium plate charged it positively. They concluded that a negatively charged particle must have been emitted from the metal. Thanks to Thomson's discovery of the electron in 1897, we now know it was the electrons that were being emitted. Let's try to explain this phenomenon and see why it is so important. Take a sodium plate and focus some red light on it. Do you see anything? No? Try increasing the intensity of your lamp. Nothing new, right? Return to the previous intensity and now change the color of the light. As you can see, when you reach a certain color, in this case green, electrons begin to emerge from the plate. If we increase the intensity now, we will see that more electrons are emitted. As you move farther into the electromagnetic spectrum, using more energetic light, the electrons start moving faster. In 1905, Albert Einstein published a paper proposing that, to describe the photoelectric effect, light should be interpreted as discrete packets of energy, known as photons, instead of as a wave. The energy of a photon can be calculated with this formula, E equals h times f, where h is Planck's constant and f is the frequency of the photon. You can also express this in terms of wavelength using the relationship c equals lambda times f, where c is the speed of light and lambda is the wavelength. Einstein discovered that when light is focused on a metallic atom, the energy of the absorbed photon equals the work function plus the maximum kinetic energy of the emitted electrons. The work function is the minimum energy required for the photoelectric effect to occur. This means that if the light isn't energetic enough, no electrons will be emitted. When the photon's energy exceeds the work function, the excess energy is transferred to the electrons as kinetic energy. Now, to determine the threshold frequency of a given material, we can divide the work function by Planck's constant. Conversely, we can calculate the work function of a material, such as sodium, by using its threshold frequency. This was a groundbreaking discovery because it implied that the energy needed to emit an electron from the atom is quantized, and so is light. We need a discrete particle of light, a photon, with sufficient energy to overcome the proton's pull and free the electron. This is why increasing the light's intensity has no effect if the individual photon's energy isn't sufficient. Thank you very much for staying until the end of this video. If you wish to learn more about quantum computing or quantum physics, check out more BQB Quantum News videos. See you!